Good day everyone. So for today we're going to have a discussion in General Chemistry 2. To be specific, we're going to discuss all about our lesson number 5 entitled Electrochemistry, and we're going to be focusing more on the reduction, oxidation, reaction, and cell EMF. Okay, so before we proceed to our discussion, let's have a quick recap all about our topic last meeting. Okay, so last meeting we have discussed all about our lesson number 4 entitled Acid-Base Equilibria and Salt Equilibria, and we have focused our discussion all about the common ion effect, buffers, and solubility equilibria. So we have known that common ion effect, by definition, so it is used to describe the effect on an equilibrium involving a substance that adds an ion that is part of the equilibrium. Okay, so next we also discuss all about the buffers. Okay, so we all know that the buffers, by definition, is a solution that can resist pH change. Okay, so it can resist pH change upon the addition of an acidic or a basic components. With the help of the neutralization of the conjugate acid or the conjugate base, it can maintain uh, its pH. Okay, so whether it's um, acidic buffer or whether it's a basic buffer, it can maintain its pH. Okay, so next we also discuss all about the solubility equilibria, and we have known that the solubility equilibria or equilibrium is the equilibrium associated with dissolving solids in water to form aqueous solution. So with that, we're gonna be having a new lesson for this afternoon. Okay, so with that, we're gonna be discussing all about the electrochemistry, and we're gonna discuss as well the reduction, oxidation reaction, and the cell EMF. Okay, so let's define first what is electrochemistry. Okay, so as an overview, electrochemistry is a chemistry that deals with electricity and its relation to chemical reaction. So with that, some reaction proceeds spontaneously and produce a small amount of energy in the form of electromotive force, while some are non-spontaneous reactions that require energy for the reaction to push through. Under the chapter in the subject introduced is the reduction and oxidation. Okay, so we remember that reduction and oxidation, or the redox reaction, is a chemical reaction where loss or gain of electrons is involved. Okay, so the field of electrochemistry has evolved to yield significant insights on the fundamental aspects of the redox chemistry, as well as a wealth of technology ranging from industrial scale metallurgical process to robust rechargeable batteries for electric vehicles. So with that, in this module, the essential concept of electrochemistry will be addressed. Okay. So with that, here are the objectives for today's discussion. So with that, at the end of this lesson, you're expected to number one, define oxidation and reduction reaction. Number two is to balance redox reaction using the change in the oxidation number method. Number three is to identify the reaction occurring in the different parts of the cell. Number four is to define reduction potential, oxidation potential, and cell potential. Okay, so next is to calculate the standard cell potential. Number six is to identify a reduction and oxidation reaction and the reducing and oxidizing agent. Number seven is to solve for the net electromotive force of a given reaction using standard reduction potentials. And lastly, is to show self-reliance while working independently. Okay, so again, those are the objectives that we need to attain as we go on through our discussion. Okay, so next we have here our test yourself. Again, test yourself is intended for us to know if you have prior knowledge all about the topic. But since we're not going to meet right now, okay, because of the graduation pictorial, okay, so I'll be the one to answer it. Okay, so what is a battery? Give two examples of battery that you use at home. Okay, so always remember a battery is a device that is responsible for storing chemical energy and converts it to electrical energy. Okay, so with that, the two batteries that we can use at home is the first one is the rechargeable battery. So it is commonly used in our gadgets such as cell phone, tablets. Okay, so that is rechargeable battery. Well, for our laptops, we are using the lithium batteries. Okay, so lithium batteries powers appliances that draws too much power, such as the laptops or a desktop. Okay, so with that, those are two examples of battery that we can use at home. Okay, so next, we have here the terms that we're gonna encounter as we go on to our discussion. Again, we have here the terms we're gonna encounter as we go on to our discussion. So, on this module, you will encounter these important terms later on. Okay, so first one is the anode. Okay, so anode is the electrode where oxidation occurs and where electrons are given up to be transferred to the cathode. While the cathode, on the other hand, it is where the reduction occurs or where the electrons are accepted. Okay, next we have here the electrode potential. Okay, so it quantifies the tendency of an electrode to undergo the process of reduction. Next, we have here the oxidizing agent or the oxidant. Okay, so oxidant is the one that accepts the electron from the substance undergoing the process of oxidation. Okay, so next we have here the reducing agent or the reductant. Okay, so it is the one that gives up electrons to another substance undergoing through the process of reduction. Next, we have here the standard electrochemical cell potential or the cell EMF. Okay, so it is the difference of the standard reduction electrode potential of the cathode and then the anode. Okay, so next we have here our discussion. So again, these are the terms that we're gonna encounter as we go on to our discussion later on. Okay, so next we have here our discussion. So first one, let's discuss all about balancing redox reaction. Okay, so always remember that in balancing redox reaction, both the reduction and oxidation reactions involve the electron transfer from one half reaction to the other. To express the electron transfer correctly together with the compounds involved, you must know how to balance redox reaction. So there are two methods that can be used. First one is the oxidation number method, and the second one is the ion electron method. So in the oxidation number method, uh, directly we can balance a specific chemical reaction. Okay, so we can balance it using their oxidation numbers. While in ion electron method, there are instances that we have an involvement of a basic media or acidic media, and there is also an involvement of hydrogen ions, hydroxide ion, and water molecules in order for it to be balanced. Okay, so that is the concept that you need to know as we talk about the balancing of redox or the oxidation reduction reaction. Okay, so next we have here the oxidation number method. Okay, so it can be seen from the reaction. Okay, so consider that we have a reaction Ag plus, which is an aqueous solution, plus Cn, which is solid, produces or yields a silver solid, and then Cn 2 plus, that is aqueous. Okay, so um, by assigning the corresponding oxidation number to each component, the reduction and oxidation reaction can be determined. Okay, so as you can see in here, okay, so we have Ag plus and Ag. So this is their oxidation number. For Ag plus is positive 1. Okay, well in Ag, since it's an element by itself, okay, so we're gonna be having in here an oxidation that is equal to 0. Okay, so on the other hand, we also have in here Cn, since it is also an element by itself. We're going to use 0 as its oxidation number, and we're gonna be having in here Cn2 plus that has a positive 2 oxidation number. Okay, so it can be seen from the reaction that silver gained an electron while zinc lost 2 electrons. Okay, so to balance the reaction, one must consider the law of conservation of mass and the balanced electron transfer. Okay, so as you can see in here, since silver gained only 1 electron but zinc lost 2 electrons. Okay, so a coefficient of 2 is placed before silver on both sides of the reaction. So this coefficient is determined by multiplying the reactions of electron gain by the number of electrons lost. Okay, so the same goes for the reaction of the electron loss, where is multiplied by the number of electron gained, which in the case is 1. So as you can see in here, by adding the coefficient of 2 for both sides, so we can see, or we can now have a balanced chemical reaction. Okay, so we have here 2 atoms of silver molecules, and we also have here 1 atom of zinc molecule. For the number of electrons that is gained and lost, we have here negative 2 and positive 2. Okay, so with that, we can say that under oxidation number method, we can easily balance the chemical reaction just by putting a coefficient. Okay, so next we also have here another method of balancing a redox reaction. So we have here the ion electron method. Okay, so in here, unlike in the oxidation number method where the reaction is balanced as it is, in the ion electron method, the reaction is divided into 2 incomplete half reaction and then balance it. Okay, so the first one is the oxidation half reaction, and the other one is the reduction half reaction. So this method also utilizes H2O, hydrogen ion, or hydroxide ion, depending on the acidity or the basicity of the solution, to balance the excess oxygen and hydrogen in the equation. So to illustrate this method, let us use the equation Cr3 plus aqueous plus MnO4 negative aqueous yields or produces Cr2O7 2 negative aqueous plus Mn2 plus aqueous. So to start balancing the reaction, divide it into 2 sets of half reactions. So the first one is the reduction and the other one is the oxidation. Okay, so as you can see in here, MnO4 negative has an oxidation number that is positive 7. And then next naman, we have here an Mn2 plus. Mn2 plus that has an oxidation number that is equal to positive 2. So always remember that reduction is gain, and in oxidation, so Cr3 plus has the oxidation number that is equal to positive 3, while Cr207 or O7 rather, 2 negative has an oxidation number that is positive 6. So always remember that in oxidation, we are losing an electron. Okay, so again, reduction is gain, okay, and then oxidation is lost. So that is oil rate. Okay, so again, oxidation is loss, reduction is gain. Okay, so next we're gonna be doing is to balance each half reaction by balancing first the element other than oxygen and hydrogen. Okay, so in here we're gonna be balancing the reaction, both the reduction and oxidation reaction, and we're not gonna be balancing all of the oxygen and hydrogen elements. Okay, so next we have here, assuming that in this ion electron method example, we have the acidic media. So if we have the acidic media, we're gonna be using water molecules and hydrogen ions in order to balance oxygen and hydrogen respectively. Okay, so as you can see in here, in the reduction half reaction, since 4 atoms of oxygen are missing on the right side, 4 moles of H2O or water molecules is added to the right side. Okay, so to balance out the hydrogen from H2O, 8 moles of hydrogen ions was added to the left side. So a similar procedure was done to the oxidation half reaction, except that a coefficient of 2 was placed to Cr3 plus to balance Cr2O72 minus or negative 2. Okay, so right after that, okay, so right after adding hydrogen or water molecules and hydrogen ion molecules, okay, so we're gonna be balancing the charges by adding electrons to the side with the higher overall positive charges. Okay, so as you can see in here in the reduction, okay, so we have here positive 7. Okay, so it produces, or we have here positive 2. So with that, the electrons that has been lost is 5 electrons. Okay, so next we have here for the oxidation, we have here positive 6 and then positive 6 electrons. So overall, we're gonna be losing 12 electrons. Okay, so right after that, okay, so in order for us to balance it, okay, so we're gonna be placing here 6 and 5. Okay, so to balance the electrons lost and gained, multiply two half reaction by an integer so that the number of electrons lost in oxidation is the same as the gain in reduction. Finally, add the two half reaction right after multiplying it by a specific integer. So as you can see in here, the reduction is multiplied into 6 and the oxidation is multiplied into 5. Okay, so finally add the two half reaction and cancel out species appearing on both sides, and after that we're gonna be simplifying the equation. So as you can see in here, all you need to do is to multiply the oxidation half reaction by 6 and 5 on the on the reduction side we're gonna be multiplying 6, and on the oxidation reaction we're gonna multiplying 5. Okay, so we have here 6 MnO4 O4 negative aqueous plus 48 hydrogen ion aqueous plus 30 electrons produces 6 Mn2 plus aqueous plus 24 H2O liquid. So next we have here the oxidation 10 Cr3 plus or positive 3 aqueous plus 35 H2O liquid produces 5 Cr207 or O7, -2 aqueous plus 70 hydrogen ions, aqueous, okay, plus 30 electrons, okay. So we're gonna be canceling out first the electrons. Right after that is to simplify like units, okay. So first one, let's simplify H2O. The number is 24 and then 35. And next we have here, let's simplify the hydrogen ions. Okay, so next we're gonna be having our final answer. Okay, so we have here 6MnO4 negative aqueous plus 10 Cr3 or positive 3 aqueous plus 11 H2O liquid produces 6Mn2 positive or positive 2 aqueous plus 5 Cr207 2 negative aqueous plus 22 hydrogen ion for aqueous. Okay, so this is now the balance equation under an acidic media. Okay, so as you can see in here, we have added hydrogen ion and water molecules in order to balance the overall reaction. Okay, so next we have here another example. So this is an example wherein we are balancing a redox equation in basic solution. Okay, so in here, okay, so first one, we have here a chemical equation that has Cn plus NO3 negative produces Cn2 plus NO2. So for the solution, first we need to determine the oxidation number. Cn, since it's an element by itself, so we have 0. Okay, NO3 negative, we have here positive 2 minus 2, and then Cn2 plus, so we have here positive 2. Okay, so right after that we have NO2, we have positive 4 and negative 2. Okay, so figure out, next that we're gonna do is to figure out what is being reduced and oxidized. So as you can see in here, zinc is oxidized. Okay, so again, oxidize or oxidation is loss of electron. Okay, so next we have here, so as you can see in here, from 0 it became positive 2. So mean to say, nag-loss siya ng negative ng 2 electrons. Okay, so next is on this one. So as you can see in here, NO3 negative has positive 2 minus negative 2. So we're gonna be having positive 3. And NO2, so we have positive 4 and negative 2. So we're gonna be having positive 2. Okay, so with that, nitrogen is reduced. Okay, so nitrogen is reduced, meaning to say it has gained an electron. Okay, so next we have here, oxygen is on both sides of the equation with the same oxidation number, so it is neither oxidized nor reduced. Okay, so right after that, we're gonna be writing the half reaction na nakuha natin kanina. So for the oxidation, we have Cn produces Cn2 plus. For the reaction, we have NO3 negative produces NO2. Okay, so right after that, balance the atoms of each reaction. So this is the unbalanced number of atoms. So first one, we have for the nitrogen, on the left side we have 1, and on the right side we have 1. Next is for the oxygen, on the left side we have 3, on the right side we have 2. So meaning to say oxygen is not balanced. Okay, so right after that, we're gonna be adding water molecules to balance oxygen and H plus to balance the hydrogen. Okay, so we're gonna be having 2H plus NO3 negative produces NO2 plus H2O. So in here, on the left side, so the number of nitrogen is 1. On the right side as well. Okay, so it is now balanced. So for the oxygen, so we have on the left side we have 3 atoms, and on the right side we also have 3 atoms, so that is also balanced. And for the hydrogen, so as you can see in here, we have 2 atoms of hydrogen on the left side, and on the right side we also have 2. So we can say now that this is a balanced equation already. Okay, since we do have a same number of atoms for both sides. Okay, so next we have here for the oxidation. So as you can see in here, we do have 1 atom of zinc for both sides, both the left side and then the right side. Okay, so it is now balanced already. Okay, so next. Okay, so right after that, we're gonna be adding electrons to balance the charges. Okay, so for the reduction, so we have +2, -1 for the left side, and on the right side we have here 0, and then next we have here +1 on the left side and 0 on the right side. Okay, so next we have here we're gonna be doing in here is to add electrons. Okay, so in here we're gonna be adding 1 electron. Okay, so 1 electron to the left. Okay, so we're gonna be having +2 -1 -1. Okay, so we're gonna be having 0 as the charges of the reduction on the left side as well as on the right side. Okay, so next we have here for the oxidation. So as you can see in here, we are going to add 2 electrons on the right side. Okay, so we're going to add 2 electrons on the right side. So we're gonna be having 0 on the left side, and on the right side we're gonna be having +2 -2. So +2 -2 is equal to 0. So in here we now have as well a balanced charges for the oxidation side. Okay, so we have on the right side is 0, and on the left side is 0 as well. Okay, so we now have a balanced charges for this example. Okay, so next we're going to be multiplying half reactions to make the number of electrons equal in both. Okay, so as you can see in here, for the reduction we're gonna be multiplying 2. Okay, so we're gonna be multiplying 2 in order for us to balance the number of electrons that we have in the oxidation side as well as in the reduction side. Okay, so we're gonna be having 4H plus 2NO3 negative plus 2E negative, or 2 electrons produces 2NO2 plus 2H2O. Right after that, we're gonna be adding the half reaction, canceling out stuff that appears on both sides of the arrow, or what we call like terms. Okay, we're gonna be canceling out like terms. Okay, so in here, first thing we need to cancel is the number of electrons. Okay, so we're gonna be canceling 2 electrons both from the oxidation and reduction side. Okay, right after that, we're gonna be copying. Okay, so we're gonna be copying all of the chemical compounds that is written on the right, or written on the left rather, and all of the chemical compounds that is written on the right. So we're gonna be having here Cn plus 4H plus 2NO3 negative produces Cn2 plus 2NO2 plus 2H2O. So the balance equation is acidic because H plus make it so. Okay, so therefore we need an extra step to replace H plus ions with OH negative ions to make it basic. Okay, so instead of using hydrogen ions, we're gonna be using hydroxide ions to make it basic. Okay, so another step we have here. So for HH plus, add 1 OH negative to both sides. Okay, so with that, we're gonna be adding 4 hydroxide on both sides, both on the right side and on the left side. Okay, so right after that, we're gonna be combining H plus and OH negative. And right after we combine it, we're going to be having the water molecules, okay? So with that, right after combining the hydrogen and OH negative ions, we're going to be having Cn plus 4H2O plus 2NO3 negative produces Cn2 plus 2NO2 plus 2H2O plus 4OH negative. Okay, so with that, we're gonna be subtracting H2O from both sides if possible. So as you can see in here, we're gonna be subtracting 2 atoms of hydrogen in both. I mean the hydrogen monoxide or water molecules in both. Okay, so we're gonna be having the final answer that is Cn plus 2H2O plus 2NO3 negative produces Cn2 plus 2NO2 plus 4OH negative, and we're gonna be doing the final checking in order for us to know if the number of atoms is correct or is balanced already, as well as the number of charges, okay, or the number of lost or gained electrons. Okay, so we have here the number of zinc for the left side is 1, as well as the right side. Okay, so for the hydrogen atoms, we have here 4 atoms on the right side as well as the left side. Okay, so for the number of oxygen atoms, we both have 8 atoms on the left and right side as well. So this balance already. Okay, so next for the nitrogen side. So as you can see in here, we do have 2 on the left side and 2 as well on the right side. So we can say now that the number of atoms for zinc, hydrogen, oxygen, and nitrogen for left and right side are both balanced, okay, or balanced already. Okay, so next we're gonna be looking if the charges is already balanced as well. Okay, so Cn has oxidation number that is equal to 0. H2O has an oxidation number that is equal to 0. 2NO3 negative has an oxidation number that is equal to negative 2. So the overall oxidation number for the left side, or what we call the reactant side, is negative 2. Okay, so how about on the product side? We have here Cn2 plus, so we have here positive 2. For 2NO2, we have 0 as the oxidation number, and for the 4OH negative, we have here negative 1 multiplied by 4, so that we have here negative 4 for the oxidation number of hydroxide. Okay, so we're going to be having positive 2 minus 4. We're going to be having as well negative 2. So the number of electrons lost and gained for both sides is negative 2. Okay, so this is now balanced already. Okay, so we can say that our final answer is correct because we have gained, or we have a product that is that gives us a balance number of atoms as well as a balanced charges. Okay, so next tayo. So let's talk about now the electrochemical cell. Okay, so in 1796, Alessandro Volta, so he's the man in this picture. Okay, so he is an Italian physicist, and he is the one who discovered that electric current may be generated from chemical reaction. So his discovery was based on previous studies made by Luigi Galvani. Okay, so he is an Italian physiologist, and he made his experimentation back in 1786. Okay, so this principle was used to create an apparatus, electrochemical cell. So we have here the electrochemical cell again. This is an apparatus that converts chemical energy from spontaneous reaction to produce electricity. It is also called the voltaic cell or galvanic cell in honor of Luigi Galvani and Alessandro Volta. So the cell actually directs the transfer of electron to an external pathway instead of directly between the reactants. Okay, So with that, okay, so this is done by physically separating two half reaction represented by the electrodes using different containers and connected by electron carriers. Okay, so always remember that several components are involved in an electrochemical cell. Okay, so the first one is the electrode or the charge carrier. Okay, so always remember that electrodes are simply where redox reaction occurs. Okay, so again, redox reaction occurs in all of the electrochemical cells. Okay, so next we also have here the anode. Okay, so the anode is the electrode where oxidation occurs. This is where electrons are given up to be transferred to the cathode, while the cathode is where the reduction occurs or where the electrons are accepted. Okay, so that is the mechanism of electrochemical cell. Okay, so with that, these two electrodes act as the site of chemical reaction. They may be in different form, but they still perform the same function. Okay, so which is to convert chemical energy from spontaneous reaction in order to produce electricity. Okay, so next we have here three types of electrode. Okay, so we have here the first one, or in figure number 2, is the inert electrode. Inert electrode, this is a type of electrode that is usually made up of carbon or graphite or platinum because carbon and platinum are inert and non-reactive to the components that undergo the redox reaction. Okay, so they only act as a site where electron transfer can occur. Inert electrodes are usually used when gases or liquids are formed as by the products of the redox reaction, since the charge carrier cannot be connected to this. Okay, so next we have here the membrane electrode. Okay, so in the membrane electrode, okay, so in this type of electrode, so this one is specialized type of electrode. So it is also called as an ion electrode or ion selective electrode or ISE. As the name implies, so this type of electrodes only detects, okay, electron transfer from or to a specific species. Okay, so an example of ISE is a pH meter, which can only detect hydrogen ions. Okay, so next we have here the metallic electrode. So this is a type of electrode that is composed of a metal strip and its metallic ion solution. In figure number 4, two metallic electrodes are used. The zinc electrode with the zinc metal strip immersed in zinc sulfate, and the copper electrode with the copper strip immersed in the copper sulfate solution. Okay, the electrons do not only act as site of the reaction but also participate in the redox reaction. They are also called as the active electrodes. Okay, so next we have here. Okay, so next we have here the standard electrode potential at 298 Kelvin or 25 degrees Celsius. Okay, so ayan, ito yung pagbabasihan natin later on. In order for us to know the standard electrode potential of a specific chemical or specific compound. Okay, so with that, cell EMF. Okay, so each electrode has its own corresponding potential. This electrode potential quantifies the tendency of an electrode to undergo reduction. Since one electrode cannot make up a cell an arbitrary electrode, the standard hydrogen electrode or the SHE was used to determine the standard electrode potential of other species. Using standard state condition as basis, the equation would be 2H plus multiplied by 1M aqueous plus 2E negative produces H2 multiplied by 1 atmospheric pressure, that is gas, is assigned as 0.0 voltage electrode potential. By placing the standard electrode as a cathode and another as the anode, the standard reaction electrode potential, or uh, E was derived. Okay, so with that, the standard electrochemical cell potential, or or the cell EMF rather, can now be computed as a difference of the standard reduction electrode potential of the cathode and then the anode. Okay, so with that, we have here an example. Okay, so let us apply this to the reaction of zinc and copper. Recall that copper underwent reduction while zinc was oxidized. Using the half reaction and their corresponding standard reduction potential, the standard cell EMF can be computed as, okay, so we have here reduction half reaction is Cu2 plus aqueous plus 2E negative produces Cu solid, and its cathode would be 0.34 voltage. For the oxidation, we have here Cn solid produces Cn2 plus aqueous plus 2E negative. For E anode, we're gonna be having negative 0.76 voltage. Okay, so with that, our net reaction would be Cu2 plus aqueous plus Cn solid produces Cu solid plus Cn2 plus aqueous. So we're gonna be having E cell is equal to 0.34 minus close and open parenthesis negative 0.76. So we're gonna be having a voltage of 1.1 voltage. So the change in the Gibbs free energy is a measure of the spontaneity of a process that occurs at constant temperature and pressure. So the EMF, or the E, of a redox reaction also indicates whether the reaction is spontaneous. The relationship between EMF and free energy is delta G is equal to negative N Fe cell. Okay, so that is the relationship between the free energy, or the Gibbs free energy, and then the cell EMF. Okay, so with that, since we have here positive as a final answer, which is positive 1.1 voltage, so we can say that this one is a spontaneous reaction. Okay, so with that, we have here E cell. Okay, so E cell can be used to determine the standard change in the Gibbs free energy of the reaction, making it possible to determine the spontaneity of the reaction at standard state. Faraday's constant, or letter F, named after Michael Faraday, is a quantity of electrical charge on 1 mole of electrons. So the value of N and F are always positive. Using this equation, delta G is equal to negative N multiplied by F and E. We can get the sign of delta G given the sign of E cell, that is, E cell is positive, G is negative, so that is spontaneous. While if the E cell is negative and the G, or the Gibbs free energy, is positive, so that is non-spontaneous. Okay, so with that, in here, just like what I've mentioned, we have here positive E, so this one is a spontaneous reaction. Okay, so another sample problem would be, so we have here, to solve the problem, we first need to balance the reaction. So the reaction is AgCl aqueous plus Ni solid produces Ag solid plus Ni2 positive aqueous plus Cl negative aqueous. Okay, so with that, we're gonna be balancing it. Okay, so we balance it by multiplying it by 2. Okay, so the cathode half reaction, multiply it by 2, and then we're gonna be adding 2 electrons on the anode side. Okay, so with that, the E of the cathode would be 0.22 voltage, and the E of the anode is negative 0.23 voltage. So for the net reaction, we're gonna be having 2 AgCl aqueous plus Ni solid plus 2 Ag plus 2 Cl negative aqueous plus Ni2 plus aqueous. Okay, so using the standard reduction potential of the two electrons, we're going to be computing the standard cell potential. So we're going to be using the equation E cell is equal to E cathode minus the E anode. So it is equal to 0.22 minus close and open parenthesis negative 0.23 is equal to 0.45 voltage. Okay, so we're gonna be inputting this value together with the other variables in the equation to solve for the Gibbs free energy. Okay, so the Gibbs free energy is equal to negative n multiplied by F multiplied by E cell. Okay, so we're gonna be having negative close and open parenthesis 2 moles multiplied by 96,500 joules divided by 1 mole for the voltage multiplied by 0.45 voltage, we're gonna be having negative 86,850 joule or negative 87 kilojoule. Okay, so always remember that it is in standard condition. Okay. Okay, so as you can see in here, we have solved for the E cell that is positive, and automatically the Gibbs free energy is negative. Okay, so with that, this example is a spontaneous reaction. Okay, so next we have here a cell diagram. Okay. Okay, so just to clarify things up, kung saan natin nakuha yung 96,500 joule. Okay, so always remember that in Gibbs free energy, or delta G is equal to negative N multiplied by F multiplied by E cell, wherein the G or the delta G is the standard change in the Gibbs free energy, while N is the number of electrons transferred per mole product during the reaction. Okay. So, as you can see in here, we have transferred 2 mole. Okay. So, next we have here the letter F. Okay, so the letter F, or the Faraday's constant, is always equal to 96,500 C per mole electron, or 96,500 joule. And the E cell, okay, so it is the calculated cell EMF, okay, or the calculated standard reduction potential. Okay, so this is where we get those values, and this is what we input in the Gibbs free energy equation. Okay, so next we have here the cell diagram. Okay, so in the cell diagram, we're going to write the reaction that is involved in a cell several times and is involved in a tedious process. So always remember that a cell diagram is the conventional notation for representing reactions. Okay, so in here, let us use the copper zinc cell reaction and convert it to cell diagram. Okay, so with that, as you can see in here, reduction is Cu2 plus aqueous plus 2E negative, or 2 electrons produces. Okay, so again, so we have here the reduction. So we have Cu2 plus aqueous plus 2 electrons produces Cu, and its E, or E cell, is for the cathode is 0.34 voltage, and for the oxidation we have Cn produces Cn2 plus, and we're gonna be adding as well 2 electrons. So for the E cell of the anode, so we're gonna be having negative 0.76 voltage, and for the net reaction, we're gonna be having Cu2 plus aqueous plus Cn solid produces Cu solid plus Cn2 plus aqueous. So for the overall E cell reaction, or the cell EMF, so we're gonna be having 0.34 minus close and open parenthesis negative 0.76, so we're gonna be having 1.1 voltage. So always keep in mind that certain information can be derived from the given half reaction and net reaction. So number 1, the copper ion reduces and forms solid copper in the cathode. Number 2, the solid zinc oxidizes and becomes zinc ion and the anode. Well, number 3, both anode and cathode are metallic electrodes. Okay, so in here, the cell diagrams can be expressed using the above information. The standard rule in writing cell diagrams can be remembered by using the acronyms ABC or anode, bridge, cathode. Okay, so ABC stands for anode, bridge, and cathode. So the reaction at the anode is expressing on the left side, while the reaction occurring on the cathode is represented on the right side and are separated by a salt bridge, which is denoted by a double bar. Okay, to express the cathode and then the anode reaction, the solid component will be placed in the outermost side and the aqueous and gas component will be placed on the inner side adjacent to the bridge. Okay, so the solid and the aqueous gas component are then separated by a phase bar. Okay, or a single bar. Note that there is a change in phase as both reaction proceed. Okay, so with that, our anode would be this one, outer part. Okay, and then our cathode would be in outer part as well, and our bridge is in inner part. Okay, so since no concentration of the aqueous component was given, we designate the concentration as 1. So that is the standard concentration for all solutions. Okay, so next, right after that, we're gonna be writing the cell diagram for the following cell reaction. Okay, so for the solution step number 1. Okay, so we're gonna be dividing the cell reaction into half reaction. So the cell reaction is Cu solid plus 2Fe3 plus aqueous produces Cu2 plus aqueous plus 2Fe2 plus aqueous. So we're gonna be dividing that cell reaction into two half reaction wherein we're gonna be having the reduction as well as the oxidation. Again, oxidation is loss, reduction is gain. So the reduction would be Fe3 plus aqueous plus E negative or the electron produces Fe2 positive aqueous. For the oxidation, we're gonna be having Cu solid produces Cu2 plus aqueous plus 2 electrons. For the step number 2, we're gonna be writing the oxidation as the left hand electrode and the reduction on the right side. Okay, so we're gonna be having Cus or solid. This is what we call the phase bar, Cu2 plus aqueous 1M. And right after that, we're gonna be denoting this one, the salt bridge, as a double bar. And right after that, we're gonna be writing Fe2 plus aqueous 1M. And then right after that, Fe3 plus aqueous 1M over Pt solid. Okay? Since both Fe2 plus and Fe3 plus are in solution, a platinum electrode is used. Okay? So, if you have seen in here an iron, okay? So, an iron 2 and an iron 3 or Fe2 plus and Fe3 plus, we're gonna be using a platinum as an electrode. Okay? Right after that, so all we need to do is to set up the hop reactions together with their potential first to get the net reaction using the cell diagram for the electrochemical reaction. Okay, so in here we're gonna be having with that we're gonna be having electrode as so with that, again, we're gonna be using platinum as the electrode. Okay, so our final answer would be this one on the step 2. So we have Cus for solid, phase bar, Cu2 plus aqueous, 1M, and then right after that, the salt bridge is denoted by the double bar. Okay, Fe2 plus aqueous 1M, Fe3 plus aqueous 1M. We're gonna be having as well again the phase bar. Okay, Pt solid. So again, platinum is used as an electrode. Okay, so Right after that, we're gonna be having another example. Okay, so we have here um another example. So write the cell diagram. Okay, so write the cell diagram or set up the half reactions together with their potential pairs to get the net reaction using the cell diagram for the electrochemical reaction. Okay, so we have here Ag solid. Okay, so this is a base bar. Ag plus aqueous 1M. Next is the salt bridge is denoted by a double bar 2H plus aqueous 1M. Next is the phase bar H2G or gas 1 atmospheric pressure over or again the phase bar PT or the platinum solid that is used as an electrode. Right after that solution, for the solution, we're going to identify the reduction and oxidation reaction, and we're gonna be looking on the figure number 5 for the cell potential of the half reaction. So with that, our reduction is 2H plus aqueous plus 2E negative or 2 electrons produces H2 gas. Okay, so our E for the cathode is 0.0 voltage. For the oxidation, we're gonna be using or we're gonna be multiplying it into 2 since we have used in here 2 electrons on the reduction side. Since on the oxidation side, we only use 1 electron, we're gonna be multiplying this side or the oxidation side by 2. Okay, so Ag solid produces Ag plus aqueous plus E negative or electron multiplied by 2. So for the E cell of the anode, so we're going to be having 0.8 voltage, and for the net reaction overall, we're going to be having 2H plus aqueous plus 2Ag solid produces H2 gas plus 2Ag positive aqueous. So the overall E cell would be 0.0 minus 0.8. Okay, so we're going to be having negative 0.8 voltage. Okay, so since we have here negative 0.8 voltage, so we can consider this one as non-spontaneous. So automatically the Gibbs free on this side would be a positive one. So we're not gonna be calculating for it. Okay, so with that, for the instructions, okay, so before I proceed to the instructions, so they still have questions, clarification. Okay, so if none, here are the instructions for our activity. Okay, so our activity is comprised of 4 questions. So for a question is 10 points each. Okay, so all you need to do is to solve the following problems. Write your answer or write your solution in the space provided after each question. Okay, so no need to use the Gresa format. All you need to do is to write all of the solution or the steps necessary for that problem. Okay, so in all, this activity is 40 points. Okay, so next we have here the references for today's discussion, and that's the end of our discussion. So I hope you learned something for this afternoon. Okay, so if you have questions or concerns about the topic or about the activity itself, feel free to message me during our consultation hours. So our consultation hours is every Monday to Friday, 8 a.m. to 5 p.m. Okay, so let's call it a day. Goodbye, class. See you again next time or see you again next week. Goodbye. Thank you for listening.